In this tutorial, we're going to take a look at transformations of parent functions, and we're going to start with the quadratic function. I'll talk about some different kinds of functions in this tutorial. We're going to start with the parabola. So this is the purple one is the graph of f of x equals x squared, and the red graph here is that parabola shifted 5 units to the right. So, for example, that point there has been shifted 5 units to the right. The vertex there is 0, 0. Here it is 5, 0. And so now this is actually the graph of f of x equals x minus 5 all squared. And I'll explain why it's x minus 5. It's shifted 5 to the right. And a lot of people would think, well, why isn't it plus 5? Why is it minus 5? So because after all, this is the positive direction. So if you take a look at some points here. So for example, that point there has been shifted into this point. Translated into that point. That point there is the point negative 2, 4. And negative 2, 4 has been shifted 5 units to the right to the point 3, 4. And so, you see, in the original function, if x was negative 2, it's negative 2 that you square to get 4. Now, 2 squared also equals 4, but I'm talking about that specific point. So it's actually this negative 2 that's been squared to make that 4. Now, in order for me to put this 3 in the new function in place of x and square something to get the same 4, because you see, after all, they're the same height. They have the same y value, 4 there, 4 there. So in order for me to be able to get a negative 2 after I put the 3 in to square to give me 4, that's why there has to be a minus 5 here. Because when I put 3 in there, 3 minus 5 is negative 2 that I'm squaring to give that 4. So that's why it's minus 5 and not plus 5, because it's really, I'm putting this new x value in because it's been shifted to the right 5 units. And the only way I can actually be then, after I put the 3 in, be squaring a number, squaring negative 2 to get 4, is if there's a minus 5 here. Here's an example of another point up here. This point in the original graph is the point 39, and it's been changed into the point 89. So again, on the original function is the 39 point. On the new function, shifted 5 to the right is the 89 point. And we can see that in the points, it's been shifted 5 to the right because the 3 has been changed to 8. I've added 5 to it because it's gone to the right 5 units. And so in order, okay, so see in the original function, 3 squared gives me 9. So if I put the 8 in here, I need the minus 5 in the function in order to be squaring then 3 to get the 9. So that's why it's kind of like that 5 undoes something, I suppose, so that you can still be squaring the same number to get the same y value. Now here's another, so actually I'll talk about the green one in a moment here. So notice that if it's x minus a number, x minus a positive number, it's actually going to the right. This graph has actually been the original one, shifted 11 units to the left. And so if it's 11 units to the left, it would be x plus 11 squared here. So if it's x plus a number, it's going to the left. If it's x minus a number, it's going to the right. Just to show you, I didn't do this in the presentation, but for example, this is the point right here, 1, 1. So 1, 1, if we're going 11 units to the left, has been shifted to that point, which is negative 9. Or sorry, negative 10, 1. And let me get my arrow going in here so I can point. So you see I need the plus 11 here. Okay, so in the original function, if I put 1 in place of x, 1 squared is 1. So I need the plus 11 here in my new equation for this one, shifted 11 to the left, so that if I put negative 10 in place of x here, negative 10 plus 11 is 1, and I square that and I get this 1. Okay, so that's why it's got to be plus 11 and not minus 11. Here's some examples with the absolute value function. So this is the absolute value of x. this original purple one here. If I had the absolute value of x minus 3, again the minus, like the minus 5 up here, went to the right. This would go to the right 3 units. If I want to go to the left, let's say 7 units, so my corner here is move 7 to the left, then it'd be f of x, the absolute value of x plus 7. 7 units to the left, 3 units to the right. Now, what if we went up or down instead? Okay, I'm going to take a look at a couple of those. So this blue parabola here is the original one shifted down 8 units. So if I take a look at some points, let's take a look at this 1, 1 here. It's been shifted into this point here. Vertically translated down 8 units in this case. You can count them. 1, 2, 3, 4, 5, 6, 7, 8 units. So the 1, 1 point has been transformed into the 1, negative 7 point. So in this case, the x coordinate's the same because it's a vertical translation. So in order for my new y value to be negative 7, after I square the 1, I have to subtract 8. So that's why the equation would be f of x equals x squared minus 8. So again, for this new one here, if I put 1, see this is a vertical translation. We're affecting y, not x. So if I put 1 in place of x here, 1 squared is 1 sub minus 8 to give me the negative 7. So for a vertical translation, you have a number subtracted or added on the end. And it's actually, it actually goes, well, in this case, it's gone down 8 units, it's minus 8. Now that kind of seems the opposite of what we're doing up here, because the minus 5 went to the right in the positive direction, but here the minus 8 goes down. So there's a reason for that. See, if we rewrite this function, instead of f of x as y equals x squared minus 8, if I rearrange, I'm going to bring the 8 over or add 8 to both sides. If we actually write the 8 with the y, and we don't normally do this, but if you write it in that form, you can see that, okay, there's a vertical translation 8 down. If you write it in this form, it does seem to be the opposite, kind of like it is up here. Okay, remember the minus 5 went to the right, the plus 11 went to the left. So you write it like this, you write the number with the actual variable, then it actually is the same rule as what the horizontal above. So we don't normally write it like that, but you see the minus 8 means it goes down 8. If it was a plus, 2, it would go up 2. So here's another example. I've taken this one here and transformed it down 10 units actually. So it's at 0. The y value is 0 there. It's at negative 10 here. So for example, this point right here is the point 6, 3. And it's been transformed vertically into the point 6, negative 7. You can count that that's 6, negative 7. So it's a vertical translation. The y value has been changed from 3 to negative 7, so it's gone down 10. And so this would be the graph of the absolute value of x minus 3. Remember, it does go 3 to the right, and then down 10. The minus 10 is what takes it down. And again, if I were to rewrite this and bring the 10 over here and write as y plus 10 equals the absolute value of x minus 3, again, okay, so that means that it's gone 3 to the right. And seemingly the opposite, okay, it's x minus 3, but actually goes 3 to the right. This says y plus 10, that's actually going down 10. So if you write it with the variable again, you can see that it really is the same rule for both, although we don't normally write that number with the y variable because the y is the dependent variable we're normally solving for y. Flip over to the second page here. We're going to talk about some stretches and compressions here, and reflections too. So again, I'm going to start with the parabola and the f of x equals x squared parabola. And this is the parabola. It's said to be vertically stretched. It's steeper. It's kind of like somebody took a hold of it here and pulled it upwards, but kept the vertex at the same point. Now that's the graph. What I actually graphed is f of x equals 2x squared. And we're going to take a look at some points. Now, on the original parabola, we have the point 3, 9. And is vertically stretched, so that point stretches up into, I didn't use arrows here, I didn't want the graph to get too messy, this point right here, which is the point 318. So on the original function, it's the point 39. If I put 3 in place of x, 3 squared gives me 9. On the new parabola, see, the y value has been doubled. So that's why there has to be a 2 in front of the x squared, because if I put 3 in place of x, 3 squared is 9. I need the times 2 to make that an 18. So vertical stretches, you need a number multiplied by the whole function. So this is said to be a vertical stretch factor 2, which means all the y values are 2 times as big, which is the case here. 9 doubled is 18. Now here's one that has been vertically compressed instead of stretched. It's less steep than the original. So we're comparing it to the original, not this transformed one. So for example, and I'll explain why this is f of x equals a quarter x squared. The point 2,4 in the original graph, okay, over 2 up 4, that point there, now vertically stretched, has been changed into this point, which is the point 2,1 right there. So vertically stretched means that vertically compressed means that the y values are now smaller. Notice that it's a vertical compression, so the x's are the same, it's y that's changed. Just like here, this is a vertical stretch, x's are the same, it's y that's been changed. So what do you do to 4 multiplication-wise or division-wise to change it into a 1? Well, you divide the 4 by 4 to make it a 1, or multiply by a quarter. Dividing by 4 is the same as multiplying by a quarter. So that's why there's a quarter here. So this is the graph of f of x equals a quarter x squared. The y values on this function are 1/4 the size of this function. So we call that a vertical compression factor 4. Now we can also think of this as a horizontal stretch, because here's the original graph. Okay, we've made it less steep, but it's wider. So it's like we took the points and we stretched them horizontally instead of vertically. So for example, this 2, 4 point has been stretched horizontally to that point, which is the 4, 4. That's where the 4, 4 comes from. So that point is like somebody took the graph and pulled it horizontally to make it, to stretch it horizontally. So the 2, 4 point has been changed into the 4, 4 point. So I'm referring to this as a horizontal stretch. So notice that if it's a horizontal stretch, the y values stay the same. It's the x coordinates that are changing. And so this is actually, and it's called a horizontal stretch by a factor of 2. Notice that the 2, 4 point, okay, so you see, what do I need in the function here so that if I put this 4 in instead of x, in place of x, I'm still going to get that 4. So you see, I need the half here, because in the original function, if I square 2, I get 4. So in this stretched one, horizontal stretched one, you see, if I put a 4 in place of x here, 4 multiplied by half is only 2. It's the same 2 we have here. And then that 2 squared is what gives you this 4. So for horizontal stretches, you need a fraction multiplied by x. Notice that this quarter is multiplied by the whole function. That's why it's a vertical, stretch or compression in this case, but this is a vertical stretch. Whole function multiplied by 2, whole function multiplied by a quarter. Okay, so we're talking vertical here. Here, the half is multiplied by the x before you square it, so it's actually inside the brackets here. So that's why it's a horizontal, well, in this case, stretch. There are horizontal compressions too. So here's a couple more examples, and this one isn't graphed here. Let's say we had the function f of x equals 4x squared. That would be a vertical stretch, factor 4, because the whole function is multiplied by 4. If we instead had f of x equals 2x all squared, notice the 2 is multiplied by the x inside the brackets, then that's a horizontal compression factor 2. And so basically now there's been a few examples here. So for vertical stretches, it's a whole number. Okay, 2, 4, the stretches it vertically. If the number multiplied by the whole function is a fraction, it becomes a compression. And the opposite is true for the horizontal stretches and compressions. Okay, so if it's a fraction between 0 and 1, or a decimal, then it's a horizontal stretch. If it's a whole number, okay, bigger than 1, it's a horizontal compression. Okay, so that's a couple of rules that are very good to remember, to know which is which, and if vertical is a horizontal, is a stretch, is a compression. Now a little bit about reflections now. I've taken this blue graph here and I've reflected the x-axis. So this is the opening down version of that one. And what happens when you reflect in the x-axis is you really just change the sign of all the y's. So for example, the y value there is 1, straight down here it's -1. The y value there is 4, it's -4 here. Okay, so exactly the opposite y values. So we could call this graph, and it's the same blue function I'm talking about up here. We could say it has a horizontal stretch factor 2, because that was the horizontal stretch factor 2 here, and a reflection in the x-axis. We could think of it vertically too. You could think of it as a vertical compression factor 4 because of the 1/4. Okay, and again, the negative means there's a reflection in the x-axis. So again, some more examples of transformations, and this time we're going to talk about the root function. I wanted to cover different kinds of functions in this lesson too. So it says graph each of the following. So this is the function, and we're going to start. This is the original root function. And I'm going to use tables of values here to show how to use tables of values or points to transform a graph to graph it. So this is the original function. I've chosen 3 points. I could choose more. I use 0, 0. See, the square root of 0 is 0. If I put 4 in here, the square root of 4 is 2. The square root of 9 is 3. I could use the 1, 1 point. If my graph was wide enough, I could have put 16, 4 here because the root of 16 is 4. Okay, but 3 points is enough. Now and this is referring back to like the parabola from the first page. The x plus 6 means it's gone, and I'm going to use some abbreviations now. This is a horizontal translation, 6 left. Remember, horizontal, it's the opposite. So it's x plus 6, so it goes 6 left. And the minus 2, the whole function has 2 subtracted from it, so it's a vertical translation of 2 down. So the horizontal translation affects the x, the vertical translation affects the y. So the horizontal translation, I'm going to 6 left, so I'm going to take each of these and subtract 6. So 0 minus 6 is -6, 4 minus 6 is -2, and 9 minus 6 is 3. The vertical translation 2 down reduces all the y values by 2. So I'm going to take this and subtract 2. 2 minus 2 is 0, and 3 minus 2 would be a 1. And so you can just transform a few points and then draw the new function. So if I plot -6, -2, and then -2, 0, and then 3, 1, 3, 1 will be right here, and then I can draw my new function. Now, 0, 0 is a really good point to use here because it's kind of where the graph begins and then goes to the left. So that's why it's a good point to include here. So that's what the graph of the root of x plus 6 minus 2 would look like. So there's another one here in B. Now I've got 3 tables here because this is actually a vertical stretch and a reflection, and then we have the horizontal translation. So x minus 1 is going to go 1 to the right, the plus 5 is going to go up 5. So the -2 vertical stretches and reflections are multiplied by the whole function. And you always do the different transformations, actually you do them in alphabetical order. So reflections and stretches first, and then translations. The reason for that is actually because of bed mass. Because in bed mass, after you get past the exponents and brackets, you do multiplying and dividing, the m and the d, and then the addition, subtraction at the end. So it's actually because of bed mass. So this is a vertical stretch of factor 2, and then we multiply it by -1 to make the opposite sign. So we're really, and I'm going to, so we're really taking all the y values and multiplying by -2. And so if you do that, now 0 times -2 of course is still 0. 2 times negative 2 is negative 4, and 3 times negative 2 would be negative 6. So if I were to graph this, this would be the root, the negative 2 root x function. I'm not going to graph that because it's kind of an intermediate part, because we're also going to translate it to the 1 to the right and then 5 up. So to go back to my pen here again. So the x value, because we're going 1 to the right, is going to have 1 added to it. And then the y value, because we're going up 5, we're going to add 5 to all those. So we're going to add 1 to all these. So 0 plus 1 is 1, 4 plus 1 would be 5, and 9 plus 1 would be 10. And then we're increasing all the y's by 5 because we're going up 5. So 0 plus 5 is 5, negative 4 plus 5 is 1, and negative 6 plus 5 is negative 1. And so we'll plot these points. So 1, 5 would be right there, and then 5, 1 is right there, and then 10, negative 1 is right down here. And we can draw a graph. Again, 0, 0 is where it started, so 1, 5 is where it starts, so the graph goes like this. It's upside down compared to these, again, because of the negative. There's a reflection in the x-axis. It's upside down. So that's what f of x equals negative 2 root x minus 1 would look like. Example number 3. So we have this, the red graph is the original reciprocal function. F of x is 1 over the root of x. And this blue function is a transformation of it. And we're told it's been stretched vertically and reflected in the x-axis from the parent function. So we're asked to determine a possible equation for it. So I'm going to locate a couple points in the original function. 1, 1. Again, if I put 1 in here, 1 divided by 1 gives me this 1. If I use negative 1 for x, negative 1 in here, 1 divided by negative 1 gives me a function value of negative 1. And this point, if we're told, we're thinking of it as being stretched vertically, that's been stretched into that point and this point, which is the 1, negative 2 point. And this point here has been stretched into the negative 1, positive 2 point. So notice, okay, we're thinking of it as a vertical stretch, so the axes stay the same. This number has been multiplied by negative 2 to make it negative 2, and the same thing here. Negative 1 times negative 2 is positive 2. That's why it's changed into that point. So if we think of it as a vertical stretch, y equals k f of x, k times f of x, then the k value would be negative 2. So because all the y values have been multiplied by negative 2, so that's a possible equation. Now it's not the only way to do this. You could actually think of this as a horizontal stretch too. So, and let me get my pen going here again. Okay, so we could think of that point is being changed into this one. So that's the point negative 2, comma 1. So we think of it as a horizontal. So y stays the same. So notice that the x has been multiplied by negative 2. And over here, same idea. That point's been changed into this 2, comma, negative 1 point, like that. So we could think of it as a horizontal stretch, and it's a horizontal stretch of 2, and of course the negative means it's actually a reflection in the y-axis, because it's flipped on the y-axis to the x. So we could think of it like this instead. So remember, it's a horizontal stretch, then it's a half that we're multiplying by the x. And of course, a negative here, because the signs have changed, we're multiplying by negative 2. Now this is actually the same as this, because remember remember, this line here really means the reciprocal. So actually, let me just write it like this. So that's the one on top. And the negative a half x, we could think of that as negative x over 2, which is equal to this 1 on top, this guy right here, times the reciprocal of the denominator, which is negative 2 over x. And so that ends up being just negative 2 over x, the same thing we had up top in the blue a moment ago. So I'm just trying to show that you actually could think of this in a couple different ways. When it's a reflection in the y-axis, it's the x that's multiplied by negative 1. Okay, so sometimes you might want to think of something as a horizontal reflection, horizontal reflection, a reflection of the y-axis instead of the x-axis. In the last page, we have a summary here for any function y equals f of x. The transformations are, and we'll call the number in front here a. If a is greater than 1, it's a vertical stretch. If a is a decimal or fraction between 0 and 1, it's a compression. Now, if a is negative, it's also a reflection in the x-axis. I didn't put that in here, but the negative sign means it's reflected in the x-axis. It's upside down compared to the original function. This number k here is what compresses or stretches it horizontally. And opposite rules to here. It's a horizontal stretch if a is a decimal or fraction between 0 and 1, and it's a horizontal compression if a is greater than 1. And again, if a was negative, it would be a reflection in the y-axis, like the previous example on the previous page. Now, you have to be careful here what goes left and what goes right. So here, when I say the d value, I mean just this number here. I'm not talking about that sign. So if I write out a couple of examples, let's see here. So let's say I was talking about the graph of this. So the way I wrote that, d is positive. So this would actually go to the right 4 if d is greater than 0. Now, if d was less than 0, then actually, we don't normally write it like this. I'd actually have to write the number like this. So, and we would normally write this as x plus 4. Instead of x take away negative 4, it's a double negative. So that would go left 4 units. So the rules seem odd there because of the fact that I've got this negative here. But so this goes right 4, this will go left 4. And the constant on the end, vertical translation, if c is greater than 0, it goes up that amount. If c is less than 0, it goes down that amount. So that's a summary of what all the different transformations look like. And that's the end of the tutorial.